Hello dear learners, I welcome you all to the second module on basic electrical circuits of the SWAYAM MOOC on electricity and electrical wiring. In module 1 we have covered the basic of electricity, key terms related to electricity and the concept of conductors and insulators. Module 2 is divided into 3 sessions. In this module, you will explore various components and their interconnections within electrical circuits, as well as the primary laws applied in the electrical circuits. Today, I will be introducing the components of electrical circuit. We will focus on resistors, capacitors, and in the capacitor we will discuss about the dielectric materials, inductors, switch and relay. All the electrical components are categorized into 2 types. Some are called active while some are called passive. Active components are capable of amplifying or processing an electrical signal on their own. Examples are vacuum tubes, diodes, transistors, silicon controlled rectifier, etc. Passive components cannot amplify or process signals on their own. These are, however, have a very important role to play, as the active devices can work only with the aid of the passive devices. Examples are resistors, capacitors, inductors, etc. So first let us discuss about the resistors. One of the most important components in electrical circuit is the resistor, because they are comprised of clay or carbon combination. They are good conductor and good insulators. There are 2 types of resistors. One is fixed and the other is variable. The schematic symbol of fixed and variable resistors are represented like this. The fixed resistors have a fixed value. 4 color bands are seen on the majority of fixed resistors. Each color stands for a digit and it can be translated into a number by using the standard color code which is given in this table. Here black is represent the 0, similarly brown is 1, red is 2, like this. The color bands are always read left to right from the end that has the band closest to it. The first and second band shows the values of the first and second digits respectively. The third band is decimal multiplier, that is the number of zeros to add the first 2 figures to get the total resistance. The limit of accuracy is also called tolerance, indicated the color of the 4th band. If the 4th band is not available, the tolerance is presumed to be plus or minus 20%. For example, the resistance having a color band sequence red, violet, green and gold. By using the color coding table, you can find the red and violet color has the digit of 27. The third color, that is green, value is 5. Hence 10 to the power 5 have to be added with 27. The total resistance value is now 2700000 ohm, or it can be represented as 2700 kilo ohm or 2.7 mega ohm. Now 5% of 2.7 mega ohm, it is represented as 2.7 into 5 by 100, that is 0.135 mega ohm. Therefore, the resistance should be within the range 2.7 mega ohm plus minus 0.135 mega ohm, or between 2.835 mega ohm to 2.565 mega ohm. Now let us see the variable resistors. The variable resistors are those whose resistance can be changed between 0 and a maximum certain value. They have 3 leads, 2 fixed and 1 movable. There are 2 kinds of variable resistors. One is rheostat and the other is the potentiometer. They can be wired wound or carbon type. When 2 leads of the resistor are joined, the variable resistor may be used as a rheostat. Rheostat is usually used to control current flowing through the circuit. They are generally used for high energy devices. The symbol for a rheostat is represented like this. The potentiometer or pot is a 3-terminal variable resistor with an adjustable sliding contact that determines the resistance value in the circuit. It has small variable resistance than rheostat and is more efficient. The rheostat works as a potentiometer if all the 3 terminals are used. Now, where we use the resistors? The resistors are used to limit or control the flow of current in the circuit. For example, in a simple circuit with a battery, a resistor can be added in series to reduce the current flowing to the component like an LED, protecting it from the damage. The next application, it is used in heating elements as a high resistance wires or coils, which is found in electric heaters or toasters to convert electrical energy into heat. The resistance of these elements causes them to get very hot when current passes through it. Now let us move to another passive component, that is capacitor. A capacitor is an electronic component that stores and releases electrical energy in the form of an electric field. It consists of 2 conductive plates separated by an insulating material called dielectric. When a voltage is applied across the plates, electric charge accumulates on the plates, with opposite charges building up on each plate. Capacitors are widely used in electronic circuits for various purposes, including filtering, energy storage, and signal processing. It can reduce voltage fluctuation in the circuit and blocks DC signals, but easily passes the AC signal through it. The basic structure of a capacitor. The first is plates. 2 conductive plates that store electrical charges. They are made up of metal. Next is dielectric. It is an insulating materials, for example, air, paper, ceramic, or a plastic film, placed between the plates, preventing direct electric contact and increasing the capacitance by allowing more charge to accumulate. The terminals, these are the leads or connections through which the capacitor is connected to the circuit. Now in this figure, when a voltage is applied to these plates, a current flows through it, charging up the plates with electrons, giving one plate a positive charge and the other plate an equal and opposite negative charge. This flow of electron to the plates is known as the charging current and continues to flow until the voltage across the plates is equal to the applied voltage Vc. At this point, the capacitor is said to be fully charged. Now, what is capacitance? The capacitance of a capacitor is a measure of its ability to store charge, and it is defined as the ratio of the charge stored to the voltage applied across the plates. It is measured in farad. Mathematically, it is represented as C, and C equal to Q by V, where C is the capacitance of in farad, Q is the charge stored in coulombs, and V is the voltage across the capacitor in volts. The capacitance depends on the area of the plates. Larger plates can store more charge, so they have higher capacitance. The next quantity is the distance between the plates. The smaller distance between the plates increases the capacitance. The third one is the dielectric constant. The type of dielectric materials affects how easily it can store charge. Materials with higher dielectric constant increases the capacitance. Now, types of capacitors. Like resistors, all the capacitors are also classified into two classes. One is fixed capacitor and the other is variable capacitor. Fixed capacitors further classified into electrolyte and non-electrolyte capacitors. The schematic symbols for capacitors are shown in this figure. Non-electric capacitors. Small value capacitors are non-electric or unpolarized and may be connected either way within the circuit. Ceramic capacitor is a non-electrolyte capacitor made with a ceramic dielectric. It is widely used in low-cost, low-capacitance applications like signal filtering and decoupling. Now, what is electrolyte capacitors? Having a higher capacitance but are polarized, meaning that they must be installed with the correct polarity. They are commonly used for power supply filtering. The third one is the tantalum capacitors, similar to electrolyte capacitors but more stable and reliable. Often used in the more sensitive and compact applications. Film capacitors. These capacitors used plastic films such as polyester or polypropylene as a dielectric material. It provides stable performance and long-term reliability. Next is the supercapacitors. It is also known as ultracapacitors. They have extremely high capacitance and it is used in energy storage applications. It is capable for storing large amount of energy for quick release. A dielectric is a material which has poor electrical conductivity but inherit an ability to store an electrical charge, thus exhibiting only displacement current, making it ideal to build a capacitor to store and return electrical energy. Now, dielectric constant. The dielectric constant, also known as relative permittivity, measures a material's ability to allow electric field lines to pass through it compared to a vacuum. In simpler terms, it indicates how effectively a material can store electrical energy in an electric field. The definition of dielectric constant is that a dielectric constant is the ratio of permittivity of the material to the permittivity of free space. It represents as K equal to epsilon by epsilon naught, where K is the dielectric constant, epsilon is the permittivity of the material, and epsilon naught is the permittivity of the free space. So, dear learner, after going through the resistors and capacitors, let us now test our learning by attempting the following questions. After answering these multiple choice questions, let us now move to the next topic, that is inductor. So inductor, a passive electronic component that stores energy in a magnetic field when current passes through it. Inductors consist of a coil of wire. The schematic symbol of inductor is shown in this figure. Types of inductors. Like the resistors and capacitors, all inductors are divided into two categories, that is fixed and variable. They can also be classified on the basis of their core material. They are iron core and air core inductors. The symbol for air core and iron core is given like this. The inductors can also be classified into filter shocks, audio frequency shocks, and the radio frequency shocks. Now, what is inductance? The inductance of a coil or circuit is a measure of its ability to oppose changes in current. It is defined as the ratio of the induced voltage to the rate of change of current. Mathematically, it is represented as VL equal to L di by dt, where VL is the induced voltage across the inductor, L is the inductance, which is measured in henries, represented by H, and di by dt is the rate of change of current with respect to time. Now, unit of inductance. The unit of inductance is the Henry, named after the American scientist Joseph Henry. 1 Henry is defined as the inductance that induced a voltage of 1 volt when the current changed at a rate of 1 ampere per second. Now, magnetic field and energy storage. When current flows through a conductor, it creates a magnetic field around it. In an inductor, this magnetic field is stored in the coil and resists changes in the current. The energy stored in the magnetic field of an inductor is given by the formula E equal to 1 by 2 Li square, where E is the energy stored, L is the inductance, and I represents the current flowing through the inductor. Dear learner, now let us see the behavior of inductors. The first behavior is opposition to change in current. When the current in an inductor increases, the inductor generates a back EMF, that is electromotive force, to oppose the increase, effectively resisting the rise in current. Conversely, when the current decreases, the inductor opposes the decrease by inducing a voltage that tries to maintain the current flow. The next one is the inductor in AC circuit. In alternating current circuits, inductors resist the change in current by introducing reactance. It is a type of opposition that varies with the frequency of the AC signal. The inductance reactance is given by XL equal to 2 pi FL, where F is the frequency of the alternating current and L is the inductance. Pi is a constant. From this formula, we know that higher the frequency, the greater the inductive reactance, meaning inductors tend to block higher frequency more effectively. Now let us see the inductor, how it behaves in DC circuits. When an inductor is introduced into a DC circuit, it resists the sudden change in the current when the circuit is first completed. Over time, the current through the inductor stabilized and the inductor behaves like a short circuit. Dear learners, let us now see a component that is called switch. An electronic switch is a device that controls the flow of electrical current in a circuit. A switch has two states. One is on. In the on stage, the switch completes the circuit and allows current to flow through it, and the other stage is off. In this position, the switch breaks the circuit. It blocks the flow of electricity and turning the device off. An electronic switch uses the electronic components like transistors or relay to control the on-off state of the circuit. Switches comes in various types. Some of the types are: number 1, toggle switch, where a lever or button that moves back and forth to open or close the circuit. The next one is a push button switch. It has a button that when pressed open or closes the circuit. Now this is the rocker switch. It is a switch that rocks back and forth between two positions, typically used in household appliances. This is a rotary switch, a switch that rotates to different positions to select different circuits or settings. And this one is the slide switch. A slide switch is that slides along a track to open or close a circuit. Now switches can either be manual or electronic, that is controlled by some remote control. Now we come to the last topic, that is relays. Now relays are a type of switch that cannot be manually turned on or off. Instead, their on and off states are controlled by an external electronic circuit, which makes them electronic switch. They are primarily used in applications where automatic switching is needed, and the switching action is controlled by an external controlling circuit. Now relays operates based on the principle of electromagnetic induction. They consist of a soft iron core and a movable conducting arm that can move between two connecting points. The movement of the arm is controlled by a coil. When no current flows through the coil, the arm rests on one of the connecting points. When current flows through the coil, the electromagnetic field is generated, attracting the arm and causing it to move to the other connecting point. Once the current stops, the arm is released and returned to its original position, resulting on the initial connecting point. The entire mechanism is enclosed in a plastic housing which has 5 external connecting points. 2 of these are connected to the relays driving circuit, while the other 3 are used for switching. One of the 3 is the movable arm known as the common point of the relay, and the other 2 are fixed points where the arm can rest. The common point and one of the fixed point are connected to the circuit for which switching is required. Dear learner, having covered the electrical inductors and inductance as well as switches and relays, it is the time to test your understanding with a few questions. I hope you have successfully answered these multiple choice questions. Now let us quickly recap the key points from today's session. I hope you enjoyed this video. See you in the next session with a new topic. Thank you very much.